3 minutes, I guess, right? Because it's not quite 9 yet.
Hi all, thank you so much for joining us today again for the second talk of Hope 2020. We have some amazing speakers and talks scheduled for the upcoming week, so please check out our schedule for the amazing talks, workshops, and villages. Our second talk for the day is Defend Your Own System Through Binary Recompilation by David King. He is currently finishing his PhD in binary security at Columbia University and is also involved in a startup called Alpha Secure. David is going to talk about binary transformation and also going to introduce a new tool called Egalito. David, let's begin.
Hi there, I'm David, and I'm here to talk about defending your system through binary rewriting and binary recompilation. I'm currently working at a startup in New York called Alpha Secure, but the work for this talk was done during my PhD. I'm just finishing up my PhD now at Columbia University. I studied a lot of different binary security techniques and binary rewriting techniques as well. So let's get right into it. I'm going to talk a bit about what binaries are, in case you're not too familiar with them, and then do a quick overview of what current binary security looks like. And then we'll go into two different types of binary transformations. So what is a binary really? Well, a binary is just the compiled version of code that was written in a compiled programming language, like C or C++. So you see the example there, GCC source.c -o binary. So here, this is how we get a binary file or an executable file or machine code out of a C source file. Binaries are very widespread, and they represent a ton of the code that actually runs on computers today. Partly because, let's say you're using an interpreted language like Python, then the interpreter itself is probably written in a compiled language and therefore is a binary. As you can see with the Mickens quote at the bottom there, unfortunately, current machines are running machine code and assembly code, and they cannot run higher level languages directly. There are many different kinds of binaries. I talked about executables already, but temporary .o object files created by GCC are also a kind of binary, same file format on Linux at least. And shared libraries and static libraries could also be considered binaries. You get different ranges of metadata included in binaries as well. Full debugging info makes the program much larger, but it's great for the developer running a debugger. It's probably not going to be that way in a production environment, though, because the executables are so large. You could have symbols. You might not have symbols. You might even be obfuscated. If you're a company trying to hide how your code works from your competitors, then yeah, you're probably going to strip the symbols and you might obfuscate the code as well. A lot of tools like debuggers and profilers are going to operate on binaries and not on source code, because the source code is what the programmer wanted, but the binary is what is actually running. And those are not necessarily the same thing. Sometimes there are compiler bugs or architecture bugs or other things that get in the way. Yeah, unfortunately, though, compilation is a one-way process. You can go from source code to binary, but you can't really go from binary back to source code. The compiler gathers a bunch of information during its compilation, and it will use some of that info and then throw it away. So if you're trying to go backwards, you have to infer a lot about the original source code, and it's quite a difficult process. So in general, binaries are meant to be run, and they're easy to run. They're not meant to be modified or understood directly, and therefore it's quite hard to do either of those things. Let me just walk through the actual requirements for a binary to be able to run. The first is that all of its dependencies have to be available. So if it depends on any shared libraries, those have to be present on the system. You can create a binary that is statically linked, so it includes the libraries, doesn't require them to be somewhere else on the system. Secondly, the architecture that you are running on has to be compatible with whatever the binary was compiled for. There's a little bit of leeway here, like sometimes a 64-bit x86 machine can probably run 32-bit x86 code, but for the most part, the architectures have to match. And finally, the operating system has to support the system calls that the binary expected to be using. this isn't as stringent of a requirement as it sounds, because sometimes operating systems implement implement system call interfaces from other operating systems. So I have some examples at the bottom there. FreeBSD actually re-implemented the Linux system call interface because Linux binaries are pretty prevalent. So now you can run Linux user space binaries on FreeBSD. Wine, as in Wine is not an emulator, lets you run Windows binaries on Linux, for instance. And the way they did that was to re-implement the whole Windows system call interface along with a couple of libraries that would normally be provided by Windows, by Microsoft. Even Windows got in on this, and they re-implemented the POSIX system call interface, or the Linux system call interface, in order to get Ubuntu on Windows working. So you can now run Linux user space binaries on a Windows machine. While they're easy to run, binaries are hard to understand. And this is the main reason, is that they have free reign over their own private virtual address space. They can do whatever they want. They can load code from libraries and other files. They don't have to follow normal function calling conventions and register conventions and typical data structures. They are alone in their own personal Turing machine that will run arbitrarily many instructions, and they can do whatever they like. They're basically a black box. You can't really see what's going on inside. System calls are the only interaction with the outside world. And you can observe those. But yeah, in fact, we can show, and we'll talk more about this later, that fully understanding a binary is equivalent to solving the halting problem, which is impossible. So it sounds grim, but what can we actually observe? Well, first we can observe the system calls that a binary is trying to make. That makes sense because that's the interaction with the outside world. The Linux program strace can do that for you. We can also modify or intercept the system calls, for instance, with a debugger. Moving on to shared libraries, we can try to observe the shared library calls with something like ltrace. I have an asterisk there, though, because some binaries can be tricky. They don't have to follow the normal calling convention, and they might confuse something like ltrace. You can also try to analyze which libraries are required with the LDD tool, or change which libraries get loaded. Like, say you have multiple versions of the same library, or you want to, overload malloc for tracing purposes or something like that. And you can drill down even deeper if you want and see the individual instructions that get executed with a debugger like GDB or with RR or the tool that I wrote down there. But that, again, just tells you what instructions the binary is currently executing. It doesn't tell you what it will do in the future, and that's the hard part. I actually want to show you a quick example of shared libraries. So in this case, what I'm trying to do is take a binary from a really old Linux system and run it here. So this system is like 4 years older than the one I'm currently on, so you wouldn't really expect that to work, and indeed it doesn't. It complains about a shared library missing. You can use the LDD tool, like I said, to figure out what shared libraries a program needs. So it prints the name that the binary requested, and then where that is located on this system. There's quite a few here. This is a graphical program, so there are quite a few. There might be less on a command line program. And you can see there's a few not found ones. In fact, 4 of them. Glue and SDL are graphics related, and Boost. Well, Boost is a C++ library, and it goes through versions very rapidly, so it's pretty common to end up depending on a version of Boost that you don't have installed. But anyway, we could go run LDD on the original machine where Gorse was installed, and that would tell us the paths to these files. And then we could copy them here, and that's what I've done. You can see the libraries there, and basically we can ask the loader, we can set this environment variable here to ask the loader, hey, when you're looking for shared libraries, please also check in this directory. And that will actually make Gorse able to run. Let's see it. Yeah, so this is showing actually a Git repository. It's a visualization of the history there. This is the repository for Egalito, which I'll talk more about. And you can see Hidenori, my collaborator Hidenori, and myself just going around and modifying various files. It's just a kind of a cool little example, I guess. So you can do this in general, right? If you understand a bit about how the shared library interface works, moving binaries between machines is really no object. You can just copy whatever libraries it needs along with it. I want to caution you though against copying libc, libpthread, libstdc++, the loader itself, and some of those like lower level things, because they're tied much more closely to the version of the kernel that's running, and it usually doesn't go well if you try to copy those. I mean, you'll just get a seg fault, nothing too serious. But yeah, otherwise, it's a very, very powerful technique, and possible just because you understand a bit about how binaries are really working. So let's go on to see some resources here. Ellie's The Green Place has a lot of great articles on linkers and loaders and shared libraries and how they work. So I highly recommend you check those out. If you want some deeper reading, you can check out the venerable Linkers and Loaders book, which I've heard is quite good. So yeah, there you have it. So we've talked a bit about what binaries are and what their interfaces are. Let's go into more about binary level security. As an attacker, you're trying to get access to, you're trying to use an attack vector to provide like input to some program that's on the system. We call that like an untrusted input source. So like if you're a server, you're handling incoming requests from the internet, from anyone on the internet. That's untrusted input. If you are running a web browser, that might download JavaScript from somewhere random and then start running that. That's also an untrusted input. Same with emails, right? And it's not just programs that are directly exposed to the network or whatever. You also could imagine like downloading an archive and then extracting that archive, or printing a PDF that you've downloaded or something. And that means that more and more programs get exposed to untrusted input. So depending on your level of paranoia, you might have to worry about defending a large set of programs on your machine. And the state of binary security, well, it's pretty grim, unfortunately, because any one bug, if it's serious enough, can compromise your entire system, right? Because the programs are running as your user. If an attacker takes over that program, then they are also your user, and they can do anything you can do. And unfortunately, there are tons of bugs in software. We know this, especially in memory unsafe languages like C or C++. There's always going to be some bugs present, and if any of them are severe enough, your whole system can be compromised. So what do users do, given this is the state of security? Well, the most sane thing to do is just to make sure that all updates are installed automatically. Really, that's all it takes to secure a system pretty well. That way, if someone discovers a problem and then develops a fix, you get that fix for free automatically as part of the update process. You really only have to worry about this to a greater degree, or do binary manipulation or whatever, if you're actually the person who's developing those updates and those patches, or maybe if you're running a very critical service and trying to hot patch it, like as soon as a vulnerability gets released, you just apply a patch in RAM or something, or maybe if you're just curious. Lots of reasons to want to worry about binary manipulation. So I do want to mention though that once you've found a problem, like a security vulnerability in a binary, the easiest way to fix it is often to go back to the source code. Modify the original source code and recompile it. Or depending on the type of bug, maybe modify the compiler's source code and then recompile it just to make it not generate the buggy sequence of instructions. If you are, say, an Ubuntu package maintainer, this is definitely the way to go. You want to implement changes widely, push them to everyone. Definitely the way to go. But if you are more security conscious, unfortunately, compilers don't tend to implement state-of-the-art defenses. One reason is that compilers are very concerned with performance. No one likes it if the compiler doesn't optimize code well, or worse, slows it down. So security techniques that have more than 0% overhead tend not to be implemented by compilers. Unfortunate, but true. So let's talk a little bit about hardening. Again, this is with compilers. So if you actually just Google hardening, you'll probably find configuration level stuff first, like how to set up your firewall or how to configure your boot scripts or whatever on a Linux machine. Just configuration to kind of harden the machine, make it harder to attack. There's also a few defenses that exist at the compiler level, right? Like guarding against buffer overruns, enabling position-independent executables, and so on. These are all sort of minor defenses that help a little bit, and they have 0% overhead. So eventually the compiler did implement them. And now most Linux distributions will enable these by default on any programs that are not broken by these transformations. So that's at the compiler level, but unfortunately, attackers are much more inventive than that. Even if we just focus on memory errors for a minute, which come typically from unsafe memory unsafe languages like C or C++. What does an attack look like? There's usually two stages. The first is the attacker tries to get an initial foothold. So this might be by, doing a buffer overrun to overwrite frame pointers or overwrite a return address or overwrite a saved function pointer somewhere. Just get an initial foothold and getting the program to start doing something it was not meant to do. So there are some defenses, and we call them preventative defenses, that target this initial step. They try to make getting that initial foothold really difficult. And the second step for an attacker is to try to get to the level of arbitrary code execution. They want to go from that initial foothold to running whatever they want on the target machine. So one way you can try that is to as the attacker, inject some new code and then jump to it and start running it. Due to some existing operating system protections, that's kind of obsolete now. It doesn't really work anymore. But you can just take it to the next level and do return-oriented programming, or ROP, where you have this sequence of code you want to run, and you find small pieces of it within the existing code. You say, if I run this bit, and then this bit, and then this bit, and then that, it actually ends up carrying out the attack that I want to have happen, or the payload attached to the attack. So you can also try to make this step for the attacker difficult, and those are typically called mitigations, where the attacker did get an initial foothold, but then you're just trying to make it very difficult for them to get to arbitrary code execution. So in the research arena, there are a lot of different defenses out there. I want to mention, though, that code reuse is super powerful, right? The same way a binary is a black box because it can do whatever it wants and it's a Turing machine, once an attacker gets an initial foothold, if they're doing code reuse, they also have access to this Turing complete code sandbox that can run arbitrarily many instructions and do whatever they want. And to make life even harder for a defender, there's even automated ROP compilers that will take a sequence of code the attacker wants and figure out exactly where those pieces are and in what order to run them to carry out this attack. It's like, extremely easy as an attacker. All right, so what can the defender do? There's a couple of different categories of defenses there. Some are preventative, some are mitigations. And I want to talk a little bit about one preventative technique, control flow integrity, and one mitigation, re-randomization. So here's control flow integrity. The idea with this is that any indirect jump, you want to make sure it's going somewhere reasonable. So if you have a call instruction, you want to make sure a return instruction is going to go somewhere reasonable, like immediately following a call instruction, for example. In this example on the slide here, there's a sort function that's called from two places. And this sort function calls a function pointer like less than or greater than or something like that. This is an indirect call, and these returns are also indirect. So the CFI would be very concerned about making sure that they're going to and from valid locations, so that the return can't go like in the middle of this function and then start a ROP chain, for example. Unfortunately, though, control flow integrity comes in a couple variants, so coarse-grained, where you do some checks, but you're not too strict about them, and fine-grained. So here's an example of coarse-grained going wrong. This return statement is supposed to return to here, right? Return following a call. But maybe it's allowed to return over here. Maybe it's allowed to return over here. If your check is just, are you jumping to somewhere that immediately follows a call instruction, then those would be allowed. And there are other cases where control flow integrity, coarse-grained control flow integrity doesn't really work. And it might sound like a small detail, but that small change is enough for an attacker to build to get an initial foothold and then build a successful attack based on this. And as a preventative measure, if you get around CFI, then you're home free. You can do whatever you want. So once it's broken, you're kind of out of luck. So let's talk a bit about a mitigation technique instead. It's re-randomization. First, let's talk about the attack here. So I already mentioned ROP, where you're doing code reuse and stitching together small pieces. This is an even more powerful variant where you don't know the code layout in advance and you read it. So let's say this is a program that's sitting across the network from the attacker. So maybe it's a web server. The attacker will first trick this program into returning its own code. there are a lot of memory disclosure bugs that can enable this, and that sort of counts as an initial foothold, I guess. Then the attacker has the code, and then the attacker can say, hey, if I run this bit and then this bit and then this bit and so on, then I'll carry out the attack I want. So you create this ROP gadget chain, and then you just inject those addresses back into the original program, and the attack has succeeded. So the idea with this re-randomization is the program is called Shuffler. The defense is called Shuffler. It's actually my work from a couple of years ago. And the idea is to re-randomize the layout of the program you're defending. So move the functions to different addresses every couple of milliseconds, maybe every 10 milliseconds, for example. So then if the attacker comes along and reads the code and then runs this ROP compiler offline, a ROP compiler actually takes a bit of time to run, right? So it doesn't finish immediately. And in that time, the defender has actually moved all the code around. Then by the time the attacker finishes this computation and says, hey, I'd really like to jump here, the code is no longer there. And this means that the attack basically fails. I want to mention, of course, that this mitigation technique also has its own weaknesses. Like, it has a time bound, right, of a couple of milliseconds of where the attacker could succeed. So if the attacker can get fast enough or near enough on the network, or like do a local attack, like by injecting JavaScript that gets run in a browser or something, then 10 milliseconds might be a really long time, and more than long enough for them to carry out the attack. So there's always pluses and minuses to different defenses. So let's look at a big diagram here showing some different defenses. Here's Shuffler, the re-randomization technique we just saw. Here's a control flow integrity technique. There's basically this big trade-off between something that is easy to get to work on a system and something that's very effective. So there's a hierarchy here of what the defense might require you to change, right? Obviously, the best is if it runs straight on binaries, but you're not going to get very effective defenses if that's your setup. And the worst is having to change the source code or maybe change the compiler that the program was compiled with. But if you're willing to do that, then you can get really powerful defenses. So there are a lot of defenses out there. Most of them have more than zero overhead, so compilers don't do them. And we have sort of an opportunity to try to do them at the binary level. So let's get into this a little more. Let's talk about binary transformations, how you can do it. Okay, we talked about binaries having these interfaces, right? Like there's a system call interface that you can sort of introspect on and deal with, and there's like shared library interface where you can try to see what's happening and try to modify what's happening. But real problems tend to arise really deep in the assembly, right? They don't happen at these nice boundaries. They happen really deep inside the code. For example, there might be an integer overflow happening, or you might be able to pass a ... to a web server and then end up reading every file on the file system, or maybe there's a compiler or architecture bug like Spectre or Meltdown, and it's just like a small sequence of instructions that ends up causing a security problem. So most problems, like I said, are not at these nice clean boundaries. They're really deep inside. Okay, so we have to deal with the binary itself, but it's hard. And here's why. Because modern computers are all von Neumann machines, which means there's a single bank of RAM that stores both code and data, or a binary contains both code and data, basically. And if we are trying to reverse engineer that binary and turn it back into assembly code or whatever, we have to decide which of those bytes are code and which of the bytes are data. So here's a problem. Let's say there's a loop, and it's just running and it's code, and we're not sure if the bytes after it are code or data. Then if this loop never terminates, then maybe it's data. But if this loop terminates and then keeps running, then of course it's code. So you basically say these bytes are code if and only if the loop terminates, which basically says we were trying to solve the halting problem in order to correctly disassemble a binary. So obviously that's undecidable, and therefore binaries are really challenging to deal with. Of course, if you just have a small localized problem at a specific virtual address, then you can go in and directly modify the code bytes. You can even do it with a hex editor if you're brave. Just go in and change a couple of code bytes. That's how you can patch a known vulnerability. But often what we want to do is not fix one problem, but guard against an entire class of problems. Like, we want to fix all buffer overruns. And the way you would probably do that is by finding every buffer and adding an extra bounds check to it. So this type of systemic security transformation is called binary hardening. You want to harden against an entire class of attacks. But again, this would require us to go through the entire code and find every buffer or whatever and add a check. And because disassembly is undecidable, you really can't do this at scale. You can do the localized fixes, but you can't do hardening. At least in theory. One way we can solve this is by, of course, introducing another level of indirection. Basically, we could virtualize the original program. So we create a virtual CPU. Instead of just taking instructions and giving them to the CPU, we instead process them a little bit, change the instructions if we want to, and then let the CPU run only a small number of them, just one basic block. And then when it's done, we go back to the virtualization framework, and then it gets the next basic block, and then says, okay, CPU, you can run this now. And you have this sort of back and forth going on. You may have heard of full system virtualization before. That's like VMware, KVM, VirtualBox. What that does is provide a virtual CPU, and then you run an operating system on that virtual CPU, and then you can run user space programs on that operating system. But that's overkill for what we want. We just have a binary, and we want to virtualize it. So we can actually stay in user space and do just process-level virtualization. Valgrind is a pretty famous tool that does that. It's great for finding memory leaks. Two other tools are DynamoRIO and Pin. They're very similar. DynamoRIO is the open source one, so I'm going to talk a bit more about that. And actually, this would be my second demo, so let's get into it. Basically, you imagine you have a program like this, and you want to run it under DynamoRIO. You just do this, and it runs pretty much normally. It was slower, not that you could notice, because DynamoRIO was having to take these basic blocks and go back and forth and run them one at a time. But it's a very powerful tool because you can write these little plugins that will do things for you. They modify DynamoRIO's behavior. So here's an example of counting the function calls that were taken by ls here. So we see there's 4,000 calls, 200 some indirect calls. What's interesting though is to run this tool and see how many basic blocks there were. 100,000 basic blocks just for a little ls program. So that's how many times DynamoRIO had to go back and forth and translate a basic block. So you can see why it ends up being expensive. But it's a very powerful tool. Yeah, I'm going to say more about it, but let's go back to the slides for now. And let's talk about how you can do binary transformation. So we already saw DynamoRIO, like virtualization, right? Let's say we have this little program here, and we're trying to instrument this call instruction. We're trying to check for a null pointer so that we're not doing a null pointer dereference. So how can we do that? I already said binary patching. That's where you have a hex editor, and you're brave, and you go and you modify the bytes directly. You have to find space for new code. And because there's no space to insert new instructions here, you have to erase some previous instructions and replicate them or whatever. So it's a little messy, and but it's very simple. And if you have a single change that you want to do, it's definitely the best approach. We talked about virtualization already. The main point here is that addresses existed at a certain, or functions existed at a certain address, and then, sorry, I should do this. They existed at a certain address, and then the virtualization framework moves them to a new address so that it can add new instructions, and it has to translate all the addresses back to pretend that the functions still exist at the original addresses. And of course, it only runs one basic block at a time before going back to the virtualization framework to figure out what to do next. So a bit of overhead there for sure. And then next, we talk about binary recompilation, which was, the nominal subject of my talk. And the idea here is that you can copy the functions to new addresses, but at the same time, insert whatever code you want in the middle of a function. Now, that will change the size of the function. And that's a bit of a problem because that means the function can't exist at its original address. You have to shift everything down. And that means you have to find all references to functions because you have to update them from old addresses to new addresses. So basically, virtualization defers that decision to runtime, right? You're dynamically translating addresses. But with binary recompilation, you're doing the whole process statically. You just figure out in advance where all the functions are so that you can change their addresses. If it sounds hard, it is. In fact, let's do a little comparison here. Patching, again, very simple. Great if you just have a single bug you want to fix. But if you do it at scale, your code will look like Swiss cheese. And it's pretty inefficient. If you are doing virtualization, like with DynamoRIO, the really big pro is that it works on any binary, right? Because it doesn't try to guess what the binary is doing. It doesn't try to figure out where the code is and where the data is. It just says, what's the next basic block you're going to run? Okay, let's run that and then go back and forth. So it is slow, but it works on every binary. Now, if we're going to recompilation, Egalito is the tool that I wrote, which you'll see more about. The big pro is that it's super powerful, right? It's as if you were back in the original compiler's backend or inside the linker. You can insert code wherever you want. You can choose addresses for functions and lay them out however you want. The big con is that Egalito, at least, doesn't work on all binaries, which just only makes sense because it's trying to do this process statically, and we know that binaries cannot be disassembled. It's undecidable. So, of course, it's not going to work on all binaries. Yeah, so here's an intro slide for Egalito. It's a binary recompiler. It's part of my PhD research. I created it over the last few years of my PhD. And it's basically binary to intermediate representation back to binary again. So it lets you do this recompilation process. And the real goal there was to let researchers create new security transformations that are too slow or too crazy to get merged into compilers. And like I said, it doesn't work on every binary. In fact, it relies on position-independent binaries. So let's go into that a little bit more here. Yeah, so binaries used to be position-dependent. So basically, inside a virtual address space, a binary used to say, I have to get loaded at this address, so that it could hardcode addresses and whatnot. And because every binary has its own virtual address space, it doesn't step on anything else. It's fine. But from a security perspective, if it can get loaded at any address, then all the pointers are less predictable, and that's great. Anyway, it used to be expensive on 32-bit x86. On 64-bit x86, it's now almost free. And once you hit that magical 0% performance overhead, of course, compilers start supporting it. And now as of 2017 or so, pretty much all Linux distributions are finally doing position-independent code by default. So pretty reasonable for Egalito to require that. We also require some exception unwind metadata, which is also now in every binary, just so that like C code can interact with C++ code. Okay, let me talk a bit about what Egalito actually looks like here. So on the right-hand side, we have what a compiler does. So you start from source code, you parse it, you create an intermediate representation, and that's where optimizations take place. Maybe you end up creating a low-level IR to like assign registers to certain variables and so on. And finally, output binaries, machine code. So Egalito starts from the machine code, creates its own IR, and then can create new binaries. And this IR can be modified internally by different security transformations or whatever. We also create a higher level IR because this is really low level. It remembers like what all the registers are and all the exact instructions and so on. So it's hard to figure out what's going on. If you're trying to do an analysis, it's much nicer to have a higher level representation. But at the same time, there's no down arrow here because we don't allow the user to modify this high level representation, because then that might actually end up meaning that a lot of instructions have to get changed. And we wouldn't know how to do that efficiently, because usually like if you change something, you make it very different, you make it much slower because the compiler was very good at optimizing. So yeah, we have this dual level representation. The low level one, read write, the high level one, read only. And okay, I've been talking about disassembly and how hard it is. So yes, the problem I mentioned, differentiating code versus data, there's some metadata that says like this is the text section and it's code and most other stuff is data. We do have two other main challenges. First is we have to, as I said, find all code pointers because we need to modify them to point to new addresses, and we have to do that statically. That's where position independent code really helps. It gives us metadata that says here's where all the pointers are. We also had to end up identifying jump tables and how many entries were in each one. And again, this is an example of the compiler throwing away information. The compiler is perfectly well aware of how many entries are in each jump table, but it only decides to output bounds checks on about half of the jump tables in a binary, because it can prove through various means that the bounds check is not actually needed. So that makes our life really hard. Only about half the time do we have a definitive answer as to how many entries there are in a jump table. Anyway, let me show you a quick demo now of Egalito. Quickly though, let me show you the speed difference between DynamoRIO and Egalito. So this is a Fibonacci program. It takes like 2.6 seconds to run. If I run it now with DynamoRIO, now all the basic blocks have to be transformed back and forth, back and forth. It's like it takes like twice as long to run. And then if I was to use Egalito to transform this and then run the program again, 2.6 seconds, it's exactly the same speed basically. So that's the speed difference between binary recompilation and virtualization. So Egalito, it is open source. It's kind of like the LLVM framework, but for transforming binaries. There's a lot of existing code, especially existing passes, which are like compiler passes. That's how you normally write code for Egalito. A pass would take in some IR, transform it however it wants, and pass it on to the next recompiler pass. So yeah, as if you're writing some C++ and doing some new defenses. But if you just want to use Egalito, you can use some of the existing defenses. So one thing I wanted to show was like running the ls program here, just transforming it. I didn't add any defenses there. I just ran it through to the recompiler, and we see that it still works. And of course, you can run a bunch of transformations there that are supported, like retpolenes, control flow integrity, shadow stacks, whatever. Let's try control flow integrity. There we go. ls still runs. And let's have a look at the code really briefly. So what the control flow integrity thing does is it finds every function that could be called through an indirect, like a function pointer invocation, and it adds this special instruction, end branch, at the beginning of that function. Now, every indirect call in the program is modified so that before it happens, you check to make sure that the place you're about to jump to actually has an end branch instruction. So this basically is a coarse-grained control flow integrity scheme, right? We make sure that every call is going somewhere somewhat reasonable, but really it could go anywhere to any function whose address is taken. Still, it's a pretty cool little transformation. What else? Oh yeah, I wanted to show very briefly this shell, which basically is like a GDB shell or something. It lets you look around and look at the IR. Like I can go into the functions, I can see what code is in this function, and it lets you kind of interactively examine the IR and see what's happening inside Egalito. So pretty cool. What next? Well, I want to show some results from running Egalito. So here's some speed comparisons between DynamoRIO and Pin, which are both pretty slow, pretty high overhead. And again, this is because they have to go back and forth, transform the basic blocks. And Egalito does all of its transformations ahead of time, produces a new executable. So it's very good performance. In fact, if you turn on our optimizations, you can even be faster than the original in some cases. So yeah, and we have tested Egalito on a lot of different executables. This was 800 or so. I got the compiler to tell me what the compiler thought was in the program, and then same with Egalito, and Egalito was right almost all the time. After that experiment, we actually took all of the programs in Debian, pretty much, which is a lot, and tried analyzing them, and that worked pretty well too. This is like the analysis half, right? If you're actually changing the binary, that is a little bit less effective. Here we took like a number of Debian packages and then tried to see if the packages would pass the package tests after the transformation. That's only at 60% right now. Part of that is because of brittle tests. Like some of them will break if you actually like change the size of the executables and things. But some of it's just because binaries are really strange and they're black boxes and it doesn't work all the time. Unfortunately, I wish it would, but that's the trade-off you make. Egalito will be really nice and really efficient, but it might not work when you first try it on a binary. So you have to work with the framework and see what the binary is actually doing. If you just want it to work right away, then you should use something like DynamoRIO, because the virtualization there is slow, but it means it will work all the time on every binary. Anyway, if you want to try some of these evaluations yourself or transform your own binaries, please do clone Egalito or download our virtual machine and run some experiments there. Bunch of different built-in tools. We saw the control flow integrity in that previous example. I don't want to say too much more about any of these, I guess. Yeah, and Egalito has been published at an academic conference, ASPLOS of this year. So you can go read our paper there, and the video from that conference is a bit more technical, and you can learn more about it. It's open source. Please download it, and if you use it, you should join our Slack where we can help you debug things and so on. Just send me an email, and I'll add you to our Slack. So in summary, yeah, lots of binary defenses are not integrated into compilers because they have more than 0% overhead, and because they're pretty complicated. So compilers don't want to be responsible for that. If you want to manipulate a binary, you can do so easily at its interfaces, like at the system call layer and the shared library layer. But if you want to go inside and modify its internals, and you don't want to just patch it in a hex editor or whatever, then you have to either virtualize the instructions or use a recompiler if the binary is amenable to that. So in conclusion, users really can try to fix binary level issues and harden their own system against attack if they so choose. So that's all I have. Thank you very much for listening.
Well, we're back live, and I'm here with David. Thank you so much for that talk. This is a talk that that really has some technical depth to it, and I appreciate you sharing your knowledge. Why don't you give a little summary or anything you'd like to highlight about the talk? And we have one or two audience questions then that I'll present to you.
Sure, yeah. I think one of the main things I wanted to focus on with this talk was to give the audience an idea of the breadth of different types of binary techniques that exist. Not just talk about my tool, but also say, here's kind of some of the other things that people are doing. And yeah, I also want to say that although binary analysis seems to be dying a little bit because computers are getting faster, it's easier to recompile code and so on, there's always a place for it, especially in larger organizations that really care about attacks, or security researchers, or anyone who's sort of extra concerned about the security of their devices. Do you have some audience questions there?
Yeah, it's been a fascinating talk. I've been watching the live chat, and I invite people that are watching on the live stream in the Matrix chat. There's still time to submit questions. We have time for a few. This first one is a question about reproducible builds. So the question is, how does this talk fit in with reproducible builds? And is this something we would do instead of using reproducible builds?
So reproducible builds is when you make sure that if you recompile the same source code, you get exactly the same binary as output. So there's no non-determinism in the compiler, basically. And that's extremely helpful, especially if you're like running a big open source project and you want to have a big compile farm to compile new versions of your code, like Debian or Ubuntu would do. Because that way it doesn't matter which machine compiles the code, it will still be the same binary as output. And it's great for verification purposes as well, because you can show that no one messed with the code during the process. That's sort of orthogonal to what I'm trying to do here. So you can make Egalito be deterministic. It, in fact, is deterministic by default. So if you were to recompile a binary and do that again on a different system, you would get similar results. But usually, most of the properties that you think about being nice about binaries, like the hashes stay the same. You can do signing on it or signature verification. All that goes out the window once you start doing binary recompilation, right? If I rewrite a binary, its hash changes, absolutely. And any signature mechanism that was used to prove that it hadn't been tampered with is not going to work, because in fact it was tampered with. So I think there's sort of orthogonal things. One is to make sure that the compiler wasn't messed with, and recompiling is to change the behavior of the code, have access to the full recompilation from source all the way to binary again.
It's fascinating. Yeah, the reliance on confirming that the code hasn't changed is clearly sort of at odds with some of this technique. So we have another question here. It is, how do these techniques, and I think you touched on it a bit, is how do these techniques apply to systems using code signing?
Yeah, so it's a good question. So first of all, code signing can actually get in the way in multiple ways. So, like I was asked at one point, can I use my recompiler to modify code that runs on Cisco routers, certain Cisco routers? And the answer was no, because they use hardware attestation all the way up, and they just won't run any unsigned code. And I was like, unless we get cooperation from Cisco and get them to sign this modified binary, it's just not going to run. So you always have that challenge. But if if the recompiler is integrated well enough into the system, you can just sign the binaries after they've been recompiled, or you can add your own signature to the mechanism that's doing the signing checks. So I think it's just a matter of how deeply you are integrated into the system. And in the worst case, you can always go back to the original signing authority and say, we're doing legitimate transformations here. We need a signature from you guys to make sure that the code will keep running.
Yeah, so in some of these applications, you really need vendor cooperation because they're embedded systems or otherwise sort of locked down. We have a last one that I think is more of a curiosity, and I know you're working or you're talking here about your doctoral research, so you probably have read it. Someone mentioned the Ken Thompson paper, Reflections on Trusting Trust. I can tell that's already familiar. Maybe you might want to comment on that. And I think the audience. I'm watching the chat, and some of the audience, this is a little more technical depth than they're used to or that they're ready to deal with. But I know that the Ken Thompson paper is actually pretty accessible. Maybe you have some thoughts on it.
Yeah, for sure. So Ken Thompson, very, very smart guy, obviously. I think the story started a little earlier than that, though, because basically when software was first being created and people started to see the military applications of it, one of the generals in the US Army was like, so what if someone backdoors your compiler? What if someone modifies the compiler and makes it always put a bug into the resulting code? Like, how would you notice? Because no one's reading these binaries. They just like hit enter and let the compiler do its thing and then just run it. You never investigate it. So that was just sort of an academic thing for a little while, and then Ken Thompson wrote about it. And yeah, I mean, it actually has happened in the past as well, where people backdoor the tool chain, and it takes quite a long time to notice because no one is auditing it, right? So I think that's very fascinating about binaries, is that over time, people are realizing, hey, we need to run binaries, but we also need to be able to sign binaries. We need to be able to verify where they come from. We need to make sure they're not tampered with. There's a lot of different uses that people are starting to see for binaries. And as a security researcher, I think we need to add at least a few things, one of which is like being able to disassemble and understand the binary. Like, let me give you an example. Let's say every binary shipped with a copy of some important metadata, like where the jump tables are, how many there are. You can do it in such a way that doesn't really compromise the secrecy of the code. However, it would make an analysis tool, like an antivirus program, able to fully understand the code. Imagine if an antivirus program could just fully understand statically all the code in something. And if you don't give them that ability, then they just say, maybe this is suspicious. I really think that binaries could move that way in the future, where they're sort of easy to disassemble, easy to understand, because otherwise we really can't guarantee their security.
Yeah, that's a great answer, and I think to me it's a very thoughtful type of question as well, or looking into that whole. It's not really a debate, it's more like an analysis. You really have to be thoughtful about this. We have another question, and I think we have time to take it. And your Zoom dropped out for a few moments before, but I think we got through it. But this next question is what you might expect. Someone wants to read a little more about your work, and particularly they asked about the experiments with Egalito and Debian packages, but is there a link or where would people find the best source for further information? Email?
Yeah, of course. So you could check out the academic paper. You can just put ASPLOS 2020 Egalito, or you can go to egalito.org and we link to it from there. The paper has a bunch of appendices that list various experiments, but also our virtual machine actually has fully replicatable scripts. So you can actually download the virtual machine, run a script, give it a long time, and it will download the source for all the Debian packages, recompile them, and print the results at the end. So.
Fantastic. Well, I think we're at the end of our time. We'll start getting ready for the next talk. We really thank you for being here. Good luck with finishing up all this research and your degree, and we'll look for you out on the technology and security scene with all these further tools and analysis. So thanks again.
All right, thank you very much.
Appreciate it, and we'll see you out there on the interwebs. We'll end this session
Take
now.
care.
Bye all.